Hello and welcome to this lecture series. In the last lecture, we talked about convergence of geometric series and telescoping series, and there actually we calculated the convergence of the series as well as the sum of the series by calculating the limiting value of sequence of partial sums of the series. But it is not easy to calculate the sum for many convergent series. Okay, yeah, but one can apply something like error estimation, or at times we can apply the more rigorous concepts like Fourier series to find the sum value. Okay, but for many cases there are many methods where we can check the convergence of the series without actually calculating what is the sum value. Okay, so today we are going to discuss some of the methods which allow us to calculate the convergence or divergence of the series without actually telling us to what sum value it is going to converge. Okay, so we are going to learn today three topics: the integral test, harmonic series, and P series test. Okay, which can be applied for any series with non-negative terms where you will find the convergence of this series or divergence of this series, okay, without actually knowing the sum value. So if you are given a series with non-negative terms, that means either the terms are some of the terms are zero or strictly positive, then one important result immediately comes is the non-decreasing partial sum of the series. Okay, so suppose that there is a series an is an infinite series with uh, the terms n being greater than equal to 0 for all n. So this makes sure that the terms are non-negative, and because an's are greater than equal to 0, so what happens to the partial sum? uh, then each partial sum is greater than or equal to its predecessor, because the n plus 1 partial sum is equal to nth partial sum plus an plus 1. Okay, and an plus 1 is greater than equal to 0, so that means Sn plus 1 is either equal to Sn if this is 0, or will be greater than Sn if an plus 1 is positive. Okay, so this that means that the partial sums are non-decreasing, and we can say that S1 is less than equal to S2, is less than equal to S3, is less than equal to Sn, and so on. Okay, so the partial sums form a non-decreasing sequence. Okay, and if you remember the monotonic sequence theorem, then it says that uh, if a sequence is non-decreasing bounded from above, then it is convergent. Okay, so these partial sums are non-decreasing, forming a non-decreasing sequence. So if the partial sum is bounded from above, then it automatically converges. Okay, so this immediately gives us this result that the series of non-negative terms converges if and only if its partial sums are bounded from above. Okay, because non-decreasing condition is already satisfied. So if the partial sums are bounded from above, then series will converge. Okay, for non-negative terms, if the series contain terms which are only non-negative. Okay, so now we are ready to give our first result here, the integral test, which says that let there is a sequence A and B sequence of positive terms. Suppose that the uh, points n equals f of n, where f is continuous positive decreasing function of x for all x greater than equal to n, and n a positive integer. Okay, so after some point capital N, the function uh, and the points of the sequence, they are lying at the same place for integer values, and the function is continuous positive and decreasing function of x. Okay, then the series n is equal to capital N to infinity an and the integral n to infinity fx dx both converge or diverge together. Okay, so either both converge or both diverge. Okay, so this is important in the sense that if you know that your series, if the points lie on the function and function is continuous positive and decreasing function of x, okay, then you can calculate this integral value, and if this integral gives a finite unique value, then it will converge, and so is series. Okay, and if it do not give a finite unique value, then it diverge, and so is this. Okay, so we'll prove this. Okay, so we will establish this result for n is equal to 1. Okay, and then so one can prove this for any general number n. Okay, we start with the assumption that function is a decreasing function of x, and with fn equals an for every n, because now we have taken a capital N to be 1, so it is true for every n. Okay, so that means there is a function y is equal to fx which is continuous positive and decreasing function of x. So you can see that the curve will be something like this. Okay, continuous positive and decreasing function of x, and at the integer points 1 and 2 and 3, the corresponding points will be 1 comma a1, 2 comma a2, 3 comma a3, and so on. Okay, and so that means that this height will be a1, this height will be a2, for 3 the value is a3, so this height becomes a3, and so on. At integer n, the height will be an, at n plus 1 an plus 1. Okay, so now we can do like two cases here. One is we are going to form rectangles. Okay, so one is we can make the rectangles of area a1, because this length is unit. Okay, and this height is a1, so I can form a rectangle of area a1 to the right of 1, and area a2 to the right of 2, so I can like join here like this, and then so this becomes a rectangle here of area a2 because height is a2 and this base is 1 unit. Okay, similarly rectangle of area a3, so on, a rectangle of area an. Okay, so that's one case. Second case is we can form the areas to the left of integer values, so we can form a rectangle of area a1 to the left of 1. Okay, here, and area a2 to the left of 2, so that means I will join like here, so this area will be a2. Similarly the area a3 on this side to the left of 3. Okay, so I can make the area a3 on this side or this side. Okay, and so these are two cases. Okay, let us see first if we form the areas to the right. Okay, so simply making these rectangles to the right of the point to make the area a1 from 1 to 2, area a2 for between integer 2 to 3, and so on. Area an lies to in the region n to n plus 1. Okay, So from this figure we can easily observe that the sum of the areas a1 plus a2 plus so on an, this is greater than the area under the curve y is equal to fx, where curve move from 1 to n plus 1, because there is some area which is above the curve. Okay, so the we immediately get that the sum of the areas, which is a1 plus a2 plus so on an, okay, which are areas of these rectangles, okay, it will be greater than the area under this curve, and we can write area under the curve by this integral 1 to n plus 1 fx dx. Okay, so this point to this point, that means area under curve from here up to this point here is less than the area of the rectangles. Okay, so that's one case when we made rectangles to the right of the integers. Okay, if we create the areas to the left of the integrals, that means instead of making a1 area on this side, if we make a1 area on the other side, and instead of making a2 on this side, we make a2 on this side. Okay, so if we construct these areas to the left of the integer values, okay, so with the left of point 1, if we construct a1 area, then a2 area, a3 area, and so on, the an area to the left of n. Okay, then you can see that from point 1 to n, the area of rectangles will be a2 plus a3 so on plus an. a1 will not be part of the area from 1 to n. Okay, a1 is to the left of 1. Okay, and area under the curve y is equal to fx from 1 to n will be greater than the sum of a2, a3 and an. Okay, because there is some part under the curve which is above the rectangles. So from second figure, uh, by not taking a1 area into consideration, okay, starting with this integer 1, we can easily see that the area of rectangles a2 plus a3 plus on an is less than equal to the area under the curve from point 1 to n. Okay, so area under curve from here up to here. Okay, and so if I add a1 to both sides, because a1 is greater than equal to 0. Okay, so if I add a1 to both sides, it will keep this inequality. So a1 plus this a2 plus a3 plus so on an will be less than equal to a1 plus this integral. Okay, so a1 we can add on both sides, and so from these two inequalities this integral is less than the a1 plus a2 plus an, and we have added a1 here which is less than this integral. So we can combine these two inequalities, and if you remember that a1 plus a2 plus on an is nothing but the uh, nth partial sum. Okay, so we can now combine these two inequalities. Okay, so if we include a1, that means we add a1 to both sides. So though this inequality and the previous case inequality we can combine to write that the integral is less than equal to the partial sum is less than equal to a1 plus this integral. Okay, so this immediately gives us the result, because when n becomes large, the partial sum will converge to the infinite series. Okay, and that infinite series will converge or diverge depending upon how these integrals behave. Okay, so when n becomes large, if this integral, okay, 1 to infinity fx dx, when n becomes infinity, this goes to infinity. Okay, if this is finite, then the right integral or right inequality immediately says that the partial sum or this infinite series, okay, is also finite. Okay, because this is always less than the this integral value. Okay, so if integral value when n goes large is finite, then this partial sum when n goes large is also finite. Okay, so it converges if the integral converges. Okay, and if integral diverges, then from the left inequality, okay, because the partial sum is greater than this integral, when n goes large, if this integral diverges or the value of integral is infinite, then the value of sum is also infinite, because the value of sum is greater than the value of integral. Okay, so if integral diverges or the value is infinite, the sum value is also infinite, means the sum also diverges. Okay, so like now we take say few examples here. Determine the convergence or divergence of the series n is equal to 1 to infinity 1 over n square plus 1. Okay, so you can easily see that if I define a function f(x) as 1 over x square plus 1, then the function is continuous positive and decreasing function of x. Okay, for all x greater than equal to 1. Okay, so we can apply integral test here because all the conditions are matched. Okay, uh, and for all integer values we will get an is equal to fn. Okay, so if we calculate the integral of this for n is equal to 1 to infinity, and if that value is finite, then this converges. If that value is infinite, then this diverges. Okay, so if we calculate integral 1 to infinity 1 by x square plus 1 dx, so we know the integral of this is arctan of x or tan inverse of x, with b tends to infinity 1 to b. So you can substitute the upper limit minus lower limit, so tan inverse b minus tan inverse 1, and when b goes to infinity, tan inverse b, that means tan inverse of infinity is pi by 2 and tan inverse 1 is pi by 4, so value is pi by 4. And so this integral has a finite value. Okay, that means this series also has a finite value, so this series converges. Okay, so but remember that the value of integral is not the sum value of this series. Okay, this test only says that if this gives a finite value, then the series is convergent. It does not mean that this series sum is equal to pi by 4. No, that is not true. Okay, so we can only check convergence or divergence by this method without calculating the sum value. Okay, so let us take one more example here. So determine the convergence or divergence of the series n is equal to 1 to infinity n e power minus n squared. Okay, so again if I write fx as x e power minus x square. Okay, so you can see again that it is a continuous function, uh, decreasing and positive for all x greater than 1. So we can apply integral test, and we can calculate the integral 1 to infinity x e raised to a minus x square dx. Now to solve this, we can substitute x square as a new variable, say x square as u, so 2x dx is du, which immediately converts this integrand into this. Okay, because x square is u, so it becomes e power minus u, and 2x dx is du. Okay, so x dx will be half of du, and the limits when x equals 1, so u also equals 1, so lower limit remains same. When x is infinity, when x goes to infinity, u also goes to infinity, so upper limit is also same, so limits remain 1 to infinity. Integral of exponential is exponential, so we get e raised to power minus u divided by minus 1, with this can be written as limit b tends to infinity 1 to b, upper limit b for u, then lower limit 1, so e power minus b minus e power minus 1, with b goes to infinity, uh, e power minus infinity goes to 0, so we will only get 1 by e and lower limit, so it changes sign. So what we get, 1 by 2 into 1 by e. Okay, so we get 1 by 2 times e, which is a finite value. Okay, so this integral converges, and so is this series converges. Okay, so since integral converges, we get that the series also converges. Okay, so again, just to remind you that this does not mean that this series has sum equal to 1 by 2 e. Okay, no, sum is not calculated here, only convergence is checked. Okay, now there is one very important series, the harmonic series, and the harmonic series is series 1 by n, for n is equal to 1 to infinity, which can be written as 1 plus half plus 1 by 3 plus 1 by 4 plus so on plus 1 by n plus so on. Okay, so this series is a very well known series, and it's a divergent series, and it diverges very slowly. Okay, so also you can see this, that an is 1 by n, and limit n tends to infinity, an is 0. Okay, but still the series diverges because there is no upper bound for its partial sum. Okay, so let us see this, that why we say that there is no upper bound for the partial sum. If we write this series, okay, and we group the terms in this way, that uh, this series is 1 plus half plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 so on, plus 1 by n plus 1 by n plus 1 so on. Okay, so if we combine these two terms as 1 by 3 plus 1 by 4, okay, then the next 4 terms, then the next 8 terms, then the next 16 terms, so 1 by 17 to 1 by 32. Okay, then next 32 terms, next 64 terms, and so on. Okay, so uh, 1 by 3 is always greater than 1 by 4. Okay, so we can write this term as greater than 1 by 4, and it is already 1 by 4. Okay, so means 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. Okay, similarly these four terms, okay, each term is greater than 1 by 8. Okay, so we can write 1 by 5 as greater than 1 by 8, 1 by 6 greater than 1 by 8, 1 by 7 greater than 1 by 8, and 1 by 8 is already 1 by 8. Similarly, all these terms, 1 by 9, 1 by 10, 1 by 15, all these are greater than 1 by 16. Okay, so we can write this, that this sum is greater than 1 plus half plus these two. 1 by 3 is greater than 1 by 4, and 1 by 4 is already 1 by 4. Okay, for these four terms, these terms are greater than 1 by 8, so each term greater than 1 by 8. Okay, and for next 8, each term is greater than 1 by 16. Okay, for the next terms up to 1 by 32, each term will be greater than 1 by 32. Then next terms, each term will be greater than 1 by 64, and so on. So what you see here is that the sum of these two, it will be 2 times 1 by 4, which is half. Okay, these are 4 terms 1 by 8, so it will be 4 times 1 by 8, which is half. So sum of these 4 terms is half. Okay, similarly these are 8 terms, and so 8 times 1 by 16, so sum of these 8 terms is again half. Okay, so the next term, the sum will be 1 again half plus half plus half plus half, and so on. Okay, so that means this sum is equal to 1 plus half plus half plus half plus half plus so on. Okay, so it's a if we leave the first term, it's a geometric series with the first term half and common ratio 1. Okay, and so we know that this, if you have a geometric series with common ratio 1, then it is divergent. Okay, so this series of half plus half plus half plus half is a divergent series. Okay, and because the original series is bigger than this series, okay, and if smaller is diverging, the bigger is going to diverge. Okay, so values are always greater than this, so that means this series is not bounded uh, from above, okay, the partial sum uh, of the sequence is not bounded from above, and so the original series also diverges. Okay, so the terms after first term form a geometric series with common ratio 1. Okay, and the original series is greater than this divergent series, and so the harmonic series is divergent. Okay, so you can remember this result. The series 1 by n is a divergent harmonic series. Okay, now the p series test is for the series 1 by n power p, and for p is equal to 1 it is the harmonic series, okay, which we already proved divergent. Okay, so series 1 by n power p, which is 1 by 1 power p plus 1 by 2 power p plus so on, okay, where p is a real constant. It converges for p strictly greater than 1 and diverges if p is less than equal to 1. Okay, so this is an important uh, result, that the series 1 over n power p converges if p is greater than 1 and diverges if p is less than equal to 1. Okay, so we'll prove this result. First we'll prove that it converges for p greater than 1. Okay, so if p is greater than 1, then we can write, see that if we write the function from here, fx is 1 by x power p and p is greater than 1, then it's a uh, positive decreasing function of x. So if we calculate the integral of this, okay, so integral 1 to infinity 1 by x power p dx, we can rewrite this 1 by xp as x power minus p dx. So we know the integration of this is x raised to power minus p plus 1 over minus p plus 1, limits 1 to infinity, means we can write 1 to b with limit b tends to infinity, upper limit first then lower limit. Okay, and p is greater than 1, so this is like minus common p minus 1, so we can write in denominator. Okay, so we can just take this constant out, 1 over 1 minus p, and this is 1 over x power p minus 1. When b is substituted, it is 1 over b power p minus 1 minus, when x value is 1, 1 raised to power this will be 1. Okay, and when limit b goes to infinity, because p is greater than 1, so it denominator goes to infinity, and so it, this term is 0, and so we get is minus 1 times this, so 1 over p minus 1. Okay, and so you can see that it integral gives a finite value, so the series is convergent for p greater than 1. Okay, so series converges by integral test. Just to remind that again, that the sum of the series is not the value of this integral, it only tells that this series is convergent because this integral is convergent. Okay, now we will prove that the series is divergence for p less than equal to 1. uh, for p equal to 0, okay, 1 raised to power 0, 2 raised to power 0, 3 raised to power 0, so in general 1 by n power 0. Okay, uh, by nth term test, the series is divergent. Okay, if p is less than equal to 0, the series diverges by the nth term test, because uh, an will become n power uh, m. Okay, with, if I write p as minus of m. Okay, and so limit n tends to infinity, an is non-zero. Okay, so series diverges for p values between 0 and 1, that means 1 minus p positive. Again, if we solve the integral that we just solved, okay, and in this case, because 1 minus p is positive, so this x power 1 minus p remains in the numerator, and so we can substitute the limits above, and you see when b goes to infinity, because 1 minus p is positive, this term goes to infinity. Okay, so this integral diverges, and so the series also diverges. Okay, so only case left is when p equals 1, so that we already did as a harmonic series. Okay, So for p is equal to 1, we have this series, which is a divergent harmonic series, and proof we have already done today. Okay. So what we found is that whenever p is strictly greater than 1, the series converges, but for any other value of p, that means for p less than equal to 1, the series diverges. Okay. So this is an important result. You have to remember this, because we are going to learn some more methods in upcoming lectures, and where these tests will be very useful. Okay. So I leave you with these numericals to find whether the series converge or diverge, and you have to apply uh, integral test to find the convergence and divergence in all these numericals. Okay, so I will continue with this same topic, that the finding the convergence or divergence of the series that have non-negative terms. Okay, so we'll continue with this. Okay, till then, have a very good day.